Part 3. Brief Overview of the Individualistic Homestead. This is an ideal model of the average individualistic homestead. The method presented is purely a rough example and is not intended to restrict any other designs, as every individual is entitled to build and live however they wish. Individualistic houses are built from all natural materials, avoiding plastic, petrochemical paints, synthetic fiber carpets, etc. Electricity should be generated by solar cells as well as wind and water turbines at the homestead. Fuels should be hydrogen and biodiesel manufactured by the users, electrolysis and fuel crops, themselves when possible, and used strictly as backup power. Wood or petrol-based heating oil should be avoided if possible, but if used, employ efficient burning stoves with baffled chimney systems. Food and livestock should be raised on-site by the user. Water should be from wells, rain collectors, and natural sources. Communication will be had by various wireless devices. This is not to imply a nation of farmers. It is to give people control over their welfare and life. The amount of work done in this manner for just one individual is far less than the 8-hour day of common toil. A 1,000 square foot garden worked for 30 minutes a day will feed 2 people all year. Thus, these individuals will have more time on their hands to explore higher learning and higher skills, thereby assisting to develop higher technologies. Therefore, this society will actually be a faster evolving and more technologically advanced civilization than the present world, not a nation of antisocial, uneducated mountain men, as some would suggest. Using 1 acre per person, 36.8 billion Earth acres, with the modern-day population, 6.55 billion people, translates into leaving 80% of the Earth's total land wild, thus assisting the Earth to heal itself from the ravages we have inflicted it with. 1 acre is not only enough to sustain one person, but enough to make one feel comfortable while offering sufficient space for specialty practices, such as minor metallurgy, glassworking, etc. It is a natural right to be entitled to 1 tax-free acre required to independently sustain oneself. One should not be forced to depend on or work within a society that claims ownership over God's land, especially if its practices are in conflict with one's views of right and wrong. When the option of independence is not offered, the society is practicing forced servitude, no matter how it is justified. This spread-out nature of the individualistic society impairs the mass effectiveness of enemy forces, from infantry to aircraft. Furthermore, 1. Each individual unit is self-sustaining, thus no single strategic target could shut down the many. In times of war, the individualistic homestead is never deprived of food and fuel by producing them on site. Their machines would never be useless as long as the wind blows and the sun shines, as other nations could be crippled with a single bomb to a single refinery. And 2. Many homesteads will be similar to fortified structures, as precast concrete is stronger and faster to build with when taking advantage of geothermal principles and utilizing partially submerged structures. Thus, a nation of individualists, each schooled in strategic defense, would be much more challenging to conquer as opposed to common housing plans filled with untrained citizens. Therefore, the individualist designs all zoning and building codes around self-sufficiency, renewable resources, and a strategic layout for defensive maneuvers. Lastly, there will be no need to establish any new infrastructure for the conversion to this society. This argument is utilized to combat many alternative energy solutions by fossil fuel lobbyists and their vassals. In fact, it will cause many infrastructures to be dismantled and their remains recycled for use in loftier goals. Note, all of the following are generous averages for 1 individual on 1 acre. 1 acre equals 43,560 square feet. A. Living space. 1,250 square feet of living space per individual equates to a dwelling with the dimensions of 25 by 25, having a basement and a first floor. This only removes 625 square feet from the total acre, and is spacious and comfortable for one individual. The home suggested below would cost about $52,000 unfinished, $90,000 finished, assuming $30 per square foot, and another $30,000 for an electrical system generating about 8,000 kilowatt hours per year. $15,000 wind system, and $15,000 solar, totaling $120,000 and taking less than 5 months to build. This is less than the present average purchased home. Depending on the resourcefulness of the owner, it could be a fully independent dwelling. Furthermore, there are occasionally rebates which may lower the cost of a renewable energy system. Efficiency and independence solutions. A solid concrete precast wall home, about $35,000 just for the steel and concrete, but livable in at this stage. The basement and half of the ground floor is sunken, utilizing geothermal and solar thermal principles for air and water temperature assistance. Solar thermal collectors are mounted amidst photovoltaic panels and are coupled with a geothermal loop, fed to a heat vault sunken beneath the basement, wherein also sits the hot water tank and a heat pump, possibly a stove. Strategically placed glass block over metal grating, used on the roof, minor side windows, and first floor, utilizing sun lighting all the way to the basement. B. Electricity. The average electricity consumption for a single individual is approximately 35,000 kilowatt hours per year, not used as heat, amounting to 9.6 kilowatt hours which need to be generated per day. Efficiency and independence solutions. A wind turbine producing 3,500 kilowatt hours of power over a year with average wind speeds of 10 miles an hour will cost around $13,000 for the turbine, tower, and accessories. Maximum wind turbine tower height is 88 feet in the center of a square acre with a home on a corner of the property. B. A photovoltaic solar cell system generating 35,000 kilowatt hours per year will cost about $14,000. C. Emergency and backup energy supplied by hydrogen and biofuel and other fuel, if unavoidable, generators, as well as biomass and other fuels plus excess heat vault heat, heated Stirling-type generators. E. Water turbines where applicable. F. Additional electricity will be produced by a Stirling cogenerating process wherein the heat from the winter heating will heat the engine first and then proceed to the home. Furthermore, the massive heat buildup in the vault in summer months will also be used. This electricity will be converted to hydrogen, successfully saving summer heat for the winter. C. Water. The average water consumption for a single individual is approximately 24,000 gallons per year. This includes shower and laundry. There are 7.48 gallons of water per cubic foot. Efficiency and independence solutions. 1 inch of rain over 1 acre produces 27,154 gallons of water. Most regions in the world have at least 20 inches of rain per year. In addition to the entire acre being contoured to collect rain, a 2,178 square foot section is dedicated to rain collection, if one has no well. Besides common filters within the system, all drinking water is passed through an electric distiller which requires 0.6 kilowatt hours per distilled gallon. The average individual drinks less than 400 gallons per year, amounting to a 240 kilowatt hour per year consumption. A. Rain collectors. 2,178 square foot per individual. Any non-saturatable area, funneling water to a drain leading to a detention tank, $3,000 for the storm system. A corrugated metal cylindrical tank 10 feet in diameter and 22 feet long, approximately $5,000, will hold 12,918 gallons of water. This is assuming consumption will be similar to rainfall. This system could include various methods of water transfer to the house through multiple filters, most likely by an electric pump, coupling it with a geothermal and solar thermal system, $10,000. And B. Common wells. D. Heating. The largest challenge to energy independence in winter is heating. A great deal of needed heating is removed with a fully or partially submerged house, taking advantage of solar thermal and geothermal principles. The average heat consumption in BTU affected by environment, this estimate uses the Midwest U.S. climate, is 92,790,000 BTU per year, which translates to 27,211 kilowatt hours per year. The average present-day individual and homes are not very energy conscious nor efficient, thus this figure can be reduced with little effort. The individualist and home are both a minimum of 30% more efficient than this average. Thus, the winter backup energy for heat required will be 10,000 to 16,000 kilowatt hours, or possibly less depending on the efficiency of the home and the individual, as well as the climate. Splitting the maximum up would amount to 448 pounds of hydrogen, 2,237 cubic meters, and 214 gallons of biodiesel needed, both impractical values as shown below. Therefore, the individualist employs a number of these systems in tandem to achieve a high degree of energy efficiency, if not total independence. Note, 1 BTU raises 50 cubic feet of air, 1 degree Fahrenheit. Efficiency and independence solutions. A large wind turbine will produce 31,500 kilowatt hours per year with winds of 18 miles per hour and a 100-foot tower. This is highly impractical for most and costs around $60,000. It is more feasible to utilize a smaller turbine, if your average annual wind is only around 10 miles an hour, in tandem with many other systems. B. A photovoltaic array, solar cells, will collect 10% of the solar energy in an environment. The average solar radiation is 0.42 kilowatt hours per square foot per day, or 153.3 kilowatt hours per square foot per year, making the average amount collected with photovoltaic panels approximately 15 kilowatt hours per square foot per year, or 1,814 square feet of solar panels, over $100,000, to meet the above demand, which is also impractical. Thus, this system should be used in tandem with the below devices. C. Solar thermal heat is water heated by sunlight in various ways used to transfer heat. It can be coupled with a heat vault system which stores the heat in an array of water tanks. The necessary materials are inexpensive. The temperatures within these vaults can reach over 170 degrees in summer months. D. Geothermal heat provides a consistent temperature base to water or air by utilizing the average ground temperature of approximately 50 degrees. By looping conduits repeatedly through the earth, it thus warms water or air cooler than this, and cools water or air warmer than this, saving the energy of another system from doing the same. This system can also be relatively inexpensive, not including the drilling variety. E. Heat from wood. The average piece of wood contains about 7,500 BTUs per pound, about 2.2 kilowatt hours. Burning at approximately 80% efficiency, one would need around 7.75 tons of seasoned wood per year to meet the Midwest average above. This is about 24 average trees. Thus, this method is to be minimized. F. Biodiesel burned as or with heating oil, possibly in combination with a wood oil stove within the heat vault. It would require over 4 acres of land and a good deal of effort to single-handedly produce 214 gallons of biodiesel from oil crops, and it amounts to only half of the expected efficient heat requirement, and only a quarter of the larger average. Thus, it is an impractical heating solution to rely upon. There is research into oil-producing algae that are claimed to produce 100 times the amount of conventional oil crops. This would undoubtedly change things. G. Hydrogen. To produce and store 4,475 cubic meters of hydrogen, the amount needed for winter backup, one would need 110,000-gallon storage tanks at 200 psi. This would take up an enormous amount of space and is thus also impractical. There is also roughly a 40% energy loss in converting water to hydrogen. Thus, for every 10 kilowatts one converts, one will only get 6 kilowatts back when burnt at 100% efficiency. This amounts to a feasible method to store surplus electricity, but is impractical to rely upon fully, requiring an electrical generating system 3 to 4 times the size as above, as well as storage, a $120,000 system, plus a $6,000 electrolyzer, and $2,000 per 1,000-gallon tank equals $346,000. E. Motive fuels. The average octane consumption for a single individual is approximately 1,000 gallons per year. Efficiency and independence solutions. A. An average electric vehicle can be run for 3,800 kilowatts per year to travel 15,000 miles with no other fuel needed. With current gas rates at $3 per gallon and the average U.S. gas mileage around 18 miles per gallon, this would save $2,500 per year in fuel, driving 15,000 miles, and only cost $342 in electricity at 9 cents per kilowatt hour. Therefore, octane may be abandoned. B. Biodiesel from plants and waste is marginally acceptable when there is no other alternative. It should be used as emergency and backup fuel only and produced by the user when possible. C. Surplus hydrogen is marginally acceptable when there is no other alternative. It should be used as emergency and backup fuel only, generated with the Homestead's surplus electricity by electrolysis.